Welcome once again to my YouTube channel. Today's lesson, we're going to look at chemical reactions. What are chemical reactions? Now, reaction kinematics is the study of the rate of chemical reactions. And the reaction rate can vary greatly over a large range of time scales. Some reactions can proceed at explosively fast rates, like detonation of fireworks, while others can occur at a sluggish rate over many years, like the rusting of barbed wire exposed to the element, right? So reactions that can be fast, like fireworks, or it could be very slow, taking many years, like the rusting of the barbed wire exposed to the elements, as you can see in the diagrams below. Now, reactions proceed based on some theory known as one of them is the collision theory. So what is the collision theory? To understand the kinetics of chemical reactions, the factors that affect kinetics, we should first examine what happens during the reaction on the molecular level. So according to the collision theory of reactivity, reactions occur when reactants, molecules, effectively collide, right? So the molecules have to bombard each other, collide, but not every collision will lead to a reaction, right? The collision has to be effective, right? So let's look at what effective collision means. So for an effective collision to occur, right, the reactant molecules must be oriented in space correctly to facilitate the breaking and forming of bonds and the rearrangement of atoms that results in the formation of products. So it's very important for the molecules to be oriented in a certain way so that when they collide, the bonds can be broken in the reactants with the resulting formation of new bonds, based on the orientation of the molecules. So let's look at this example. Let's say that you have the reactant A, as you can see here, reacting with reactant B to produce the product B and product AX. Okay. So let's look at the first diagram. Now, assuming that the molecule A, right, collides with the reactant BX from the side, okay, for the side of B. Now, A will be unable to combine with X to form the product AX, right? Because if it's bombarded on this side, then it's difficult for B to leave so that A can form a compound with X. Okay, very difficult for it to leave. So this collision is going to be ineffective because it will be difficult for B to leave, for A to replace it, right? Now let's look at the other scenario that can occur. Now, if the reactant A now collides with the molecule BX from the side of BX, okay, like this. Okay. This is going to be effective collision because the molecule B will be able to leave, right? If A bombards from the side of X. Then once this leaves, then you can have a reaction forming between the A, and the molecule X, okay, to give you this. Okay, so this is an example of effective collision. The molecule have to be oriented in a way such that you can have one molecule leaving and then the other one taking its place, right? So this is what we refer to as effective collision, right? So the effective collision will lead to the formation of the product, right? You have a reaction occurring, okay? So during a molecular collision, the molecules must possess a certain minimum amount of kinetic energy for an effective collision to occur. So if the energy is not enough, the collision will not be effective, right? Now, this energy varies for each reaction, and it's known as the activation energy. Okay, activation energy. Okay. So when you say activation energy, you're talking about the minimum amount of energy that is needed for the molecules to be able to break down into products or lead to formation of products. There's a certain amount of energy that's needed when they collide for this to occur, for the bonds to break, the reactants, and then to form new compounds. Okay. Now, the rate of reaction, therefore, depends on the activation energy. A higher activation energy means that fewer molecules will have sufficient energy to undergo an effective collision. So let's think about this way, using this diagram. Okay. All right, so if you have this diagram here, you have the potential energy on the y-axis. So that's potential energy. And then the reaction progress on the x-axis. Now, let's say that this is the initial energy level or the reactants. So you have the reactants here. The reactants will need a certain minimum amount of energy before they can proceed for the formation of the products. Okay, so let's say that this is the energy that they need to work. They need to have this minimum energy before the reaction can progress, right? So this minimum energy level that you need for the reaction can proceed to the formation of products is activation energy, right? So if you think about its initial point, the activation energy is the energy level here. Okay, so this is going to be the activation energy. Okay, this energy that you need here. Okay, so think about it like a hill. The products have to be pushed, sorry, the reactants have to be pushed up the hill. So they're going to get to this level here. So once they have this minimum energy level, then the reaction can proceed freely. Now you can break down easily to form the products. Okay, you have to overcome that energy level before the reaction can proceed. That is the activation energy. Okay. So this is a diagram showing you the relationships between the reactants, activation energy, and then the products. Okay. Now, when the reactants have a higher energy level than the products, then we refer to this kind of reaction as exothermic reaction. Exothermic. Okay. Exothermic means that heat is given off. During the reaction. Okay, there's heat loss during the reaction. But the reactants have a higher energy level than the products. Okay. Now we can also have a diagram for another reaction where energy is this time gained. So let's look at that. It's a gain of energy. So again, let's begin with the reactants have an energy level at this point here. Now the activation energy, they need to overcome the activation energy. And then maybe you have the products having higher energy at the end than the reactants. Okay. So when this occurs, then heat is absorbed. There's absorption of heat in this kind of reaction. Okay. So refer to this type of reaction as an endothermic reaction. So endo means heat is taken in, the absorption of heat. So we say that heat is absorbed during this reaction. So the activation energy is going to be the difference of the energy here. Okay. This will be the activation energy. So it's very good to have an idea of this type of diagrams, in your chemistry lessons or any test that you're taking on chemical reactions. Okay. Now, what are the factors that affect the rate of chemical reactions? Okay. There are four main factors that can affect the rate of chemical reactions. One, the reactant concentration is very important. Reactant concentration. Increasing the concentration of one or more reactants will often increase the rate of reaction. Okay, this occurs because a higher concentration of a reactant will lead to more collision of the reactants in a specified period, right? You have more collisions of reactants in a specified or specific time period because you have more of those reactants present. So the reactant concentration is very, very important. Increases the rate at which the reaction would occur. Okay. Now, the second factor is the physical state of the reactant and the surface area. The physical state of the reactant and the surface area. What does this mean? Now, if the reactant if the reactant molecules exist in different phases, as in the heterogeneous mixture, okay, the rate of reaction will be limited by the surface area of the phases that are in contact. Okay, let's explain this further. Okay, using an example. Now, if I have a solid metal reactant and gas reactant that are mixed, only the molecules present on the surface of the metal are able to collide with the gas molecules. Therefore, increasing the surface area of the metal by pounding it flat or cutting it into many pieces will increase the rate of the reaction, right? Okay, so once you increase the surface area by pounding, cutting to pieces, they have more of the metal surface exposed, to the gas reactant, and then the reaction will proceed a little bit faster. Okay, so that's one way in which the rate of the chemical reaction can be affected or can be increased. Right? Now, another factor is temperature. Temperature, that's the third factor. An increase in temperature typically increases the rate of reactions. Okay, so temperature will increase the rate of reactions. An increase in temperature will raise the average kinetic energy of the reactant molecules. Okay, so if we increase the temperature, see the molecules begin to move faster. The speed of the molecules increase. So once there's an increase in the speed of the molecules, there's going to be an increase in the frequency, okay, which they collide with each other. All right, it's more likely to lead to an effective collision that will cause the reaction to occur. All right, so you have a greater proportion of molecules that will have the minimum energy necessary for an effective collision to occur. All right, so the reaction rate will then increase. All right, so this is a graph that illustrates what is happening with temperature. So let's say you had a fraction of molecules on the y-axis over here and a kinetic energy on this side. Okay, so at a lower temperature, which is a blue curve over here, see the molecules, this amount of molecules that will have enough energy, okay, for the reaction to occur. Okay, assuming you have the activation energy here. Okay. Okay. So all the molecules here, that's a fraction of molecules that have energy. That will be below the activation energy. Okay. But if you increase the temperature, you see the graph becomes a bit more broader, the red one. So you see that you have fewer molecules having activation energy below like this. And then you have more molecules that will have higher activation energy. Okay. More of the molecules, it's increased the number of molecules that have activation energy for the reaction to occur. Okay. And then the fourth one is the presence of a catalyst. The presence of a catalyst. Okay. So a catalyst is a substance that accelerates a reaction by participating in it without being consumed. So catalysts just speed up the rate of chemical reactions. They are just there to speed up the rate, but they do not take part in the reaction. Right? So catalysts provide an alternate reaction pathway to obtain products. They are critical to many biochemical reactions. Though we're going to examine this later in under the topic known as catalysis. Okay, but for now, let's remember that the present catalyst will speed up the rate of chemical reaction. So basically, what the catalyst is doing is that it lowers the activation energy. Okay, lowers activation energy. So if we go back to our diagram here, this will be without a catalyst. So as we add a catalyst to this, then the reaction is going to look like this. Okay, the activation energy will be lowered. So instead of molecule going all the way up here, that because the activation is lowered by catalyst, it only has to gain this amount of energy right here. So that you see the peak has been lowered. So the reaction will be faster. It attains this activation energy faster, and then to broken into products. Okay. So that's what happens if you add a catalyst. It lowers the activation energy. So the reaction will proceed faster. So in a nutshell, this is what chemical reaction is all about. And then the factors that affect the rate of chemical reactions. I'll see you in the next video to talk more about chemical reactions and factors and other factors that can change what we call a chemical equilibrium. See you soon. Bye.